Hi guys, welcome back. And as I promised, we are finally going to finish EQ3. I apologize because I'm a little bit sick, not with that sick, but so my voice might be cracking in and out. But hopefully we can get through this and then I can get you guys ready for the quiz on Friday. Before we start, just wanted to let you guys know that continue to do your check-ins online. Those are going to be coming to you guys every morning. All of the questions on there, you guys are getting about 2 points for just putting your name down, really. You get 1 point for getting them right, and then anything after 3 is extra credit, so definitely keep turning them in. Those questions are coming straight from the test, so kind of gives you an opportunity to study for your test. Our first quiz is going to be Friday. We're going to go ahead and use that same Google platform that we've been doing the check-ins in. Seems to be working pretty well. If you guys have any questions, like an answer comes in funny or it marks it wrong, at the end of the day, I still go back and look at everybody's responses and then I autocorrect. So if it marks you wrong, just kind of keep in mind that I will be the one that ultimately submits the final grade. So don't worry about that. Tomorrow we are going to be working on our density labs that we did on Thursday of last week. Kind of seems like forever ago. But we're going to be working on those and then setting them up on a Google spreadsheet. If you missed that lab for whatever reason, please let me know either through Remind or you can email me or School Loop Mail that you need data. So you can still get credit for not doing that lab. I'll just give you some data and that way you can get the majority of your points there. So for whatever reason that might have been. So our agenda, we're going to make sure you guys did the check-in. If you haven't done it, then after this video, go ahead and do the check-in for today. We're going to finish up EQ3, do a couple of practice problems, and then I'll be posting your study guide later today as well. If you guys look at your pride and your T-cell, pretty much everything is checked off. You guys are super resilient. I appreciate you guys for being here. Totally missed you guys, seeing everyone's faces. So hopefully pretty soon we'll be back in class. But for now, let's go ahead and move on to slide 2. So for slide 2, we see that one of our forensic tests is using refractive index. Refractive index is when we measure the bending of light. So basically, when you guys flip on a light switch, that light is going to travel to your eye at a rate of about 300 million meters per second. If it's just going straight from the light bulb to your eye, then it's just passing through solid air at that 300 million meters per second. However, if you guys look on the right, so let me go ahead and mark that really quick. We have our little pencil in a beaker there. If you guys look at that, and maybe try this even at home just for fun if you're bored or anything. You can actually stick a pencil in a clear glass of water and you're going to notice that it looks kind of bent. And if you've ever kind of seen that, you might have been like, whoa, cool, I can do magic. It's not actually magic. What it is as that light enters that water, it's kind of hitting a little bit of a speed bump. And so when it does that, it's going to bend the light. So if we see here where it says deviation angle, that light is coming in at a straight line. So here it comes in right there. And then when it hits that barrier, so in this case the water, so this barrier that you guys are seeing here is actually that water right there. It's going to cause that light to slow down, just like you would if you hit a speed bump or if you tripped over a shoe or something like that. And it's going to alter the path of that light. So instead of going straight like it would have before, so I'll kind of highlight the original path. Instead of going straight like that, it's actually going to slow down due to that barrier. And now it's going to go ahead and deviate or change its path. That changing of the path is then going to make your image look bent. So when we see our pencil right here, we see that as the light was coming in, so it was kind of going in, we'll go this way actually, as it was going in there, it hit that barrier. So I'm going to go ahead and mark the barrier. The barrier is your water. Okay, so instead of going straight as it would have, it is now going to deviate. And so we're going to see it kind of bend here, going that way. And so that bend makes the pencil look bent. Is it bent? Of course not. If you pulled it right out of the water, you're going to see it straight again. But it works really well for little kids. So if you want to show them a quick magic trick, that's a cool one to do. So we're really going to focus on refractive index today. So I definitely want to make sure that you guys are really taking that one home with you. That one is going to be on the test multiple times. I am going to mention some of the other tests, but for this point, like for example, for fluorescence right there, for fluorescence, those are going to be more vocabulary. In fact, I might just take them out altogether from the test just because I want you guys to focus on the real meat and potatoes, which is going to be that refractive index and that density. So for right now, fluorescence, just to kind of let you know what it is, It's kind of like if you've ever gone and used a black light. It's when we put it under a different light source and we look for different spotting. We look for how it glows, maybe in a black light or different wavelengths to see how the fiber reacts. But like I said, we're really not going to focus too much on fluorescence, and we are really going to hit down on that refractive index. So let's go to slide 3. So when we look at refractive index from a scientific concept, just kind of taking away the speed bump, analogy there, we're going to say that it's measuring the rate at which the light slows. So when we look at the word rate, just kind of looking at our vocab there, when we look at the word rate, we're talking about speed. Okay, so if you're kind of like, what's the rate of something? We're looking at how fast or how slow it travels. I'm going to erase that because it looks a little bit, kind of takes it away. So we're looking at how fast or how slow that light's going to travel. In this case, we want to see how much does that light slow down as it leaves one medium of low density. So again, we see that density is coming back. There's density again. I'm going to go ahead and do rate. So it's leaving that medium of low density. In this example, we're saying that that's air. So we're want to make sure we know that. Air is always going to be what we're using. So unless we're in space or we're in some kind of science, super sci-fi environment, air is always going to be your answer for your top number in just a minute. So just always kind of remember that it's air. And that it's going to be entering another medium of higher density. So then whatever our light is entering, it's going to be passing through air. And then eventually it's going to hit maybe oil or water or some type of other liquid that we're going to place our fiber. We can also do this with glass. So we can do this with clear plastics. So it's a really cool application with refractive index. And so we see higher density then being our important part there. Our formula for that is going to be refractive index equals the speed of light in air divided by the speed of light in the medium. Now, like I said before, we're always going to use air, so we really want to make sure we remember this number for your quiz. And for your quiz, that number is 300 million meters per second. So that's really quick. And if you think about that, it's what we kind of consider instant. When you flip the light switch in your house, you don't have to wait for a minute for the light to actually reach your eye. It's a pretty much instant process. Why is that? Because it's traveling at such a quick rate of 300 million meters per second. Now, what is going to be our variable for speed of light? It's kind of a weird one. It's actually the letter C. So instead of saying speed of light, like using the variable S, we're actually going to say that our variable is going to be a C. So that it's going to look like that. Oops. Excuse me. It's going to look like that. So we're going to have C, and then we're going to say C of A. So C sub A, you can barely see that, but I'll do it better later on. And it's going to be over C of the medium. So that's going to be C, which is the speed of light in air, divided by C, the speed of light in the medium. So this right here, just kind of remember that when we're talking about our variables, that we're really talking about the letter C. You might have even heard Einstein's famous formula, E equals mc squared. Well, the C from that mc squared is actually the speed of light. M equals mass. E equals energy. So now you've learned a little bit of Einstein math there. You can go home and say you already are at home, but you could have gone back and told your parents, hey, look, I learned a little bit of Einstein's theory. So what does this all mean, or how do we see it with refractive index? So even though it sounds like there's a lot of math involved, and there is, at the end of the day, it's actually a pretty easy lab setting where we're going to be looking for a halo shadow. So if you don't know what a halo is, and I've kind of put it right here so you guys can kind of see. A halo, you might have think of that is not the thing that angels wear. Absolutely is. So it's that glowing ring that you get around an object that emits light. So with angels, we kind of think of them as coming from heaven, having that inner light. They're projecting that halo above their head, that ring above their head. In this case, I'm showing you guys here is the sunshine. And that sunshine, actually, this is exactly refractive index. It's emitting that light through air. And in this case, we see that air is maybe passing through smog, perhaps clouds, and it's creating that halo or ring effect around that object. So what we want to know is where is the halo going to form? Now, the halo we're going to actually refer to as the Beck line. So we want to make sure we really know that word. And the Beck line is that halo or that ring shadow that forms around an object when you place it into a liquid with a different refractive index. Okay, so again, we see that word refractive index being used. So, and we also see the word different being used. And I do want to pay attention to that different because that means we're going to be looking at more than one refractive index. So that's going to be really important when you see the diagrams in just a minute. So some things to think about. The Beck line will form on the outside of the object if the liquid has a higher refractive index than the fiber. And when I draw the pictures in just a minute, I want you to remember, why is it on the outside? So if the liquid has the higher refractive index, then that means the speed bump is going to form outside of the object because the liquid is acting as a barrier. And we'll see that in a minute with the pictures. If the Beck line is on the inside of the object, that means that the liquid had a lower refractive index, allowing that light to pass right on through, no speed bump. But when it got inside of the object, it hit that speed bump. And so now we're going to project that Beck line on the inside of our object. So that could be your fiber, your plastic, your piece of glass. What happens if they have the same refractive index? So if we have a piece of plastic that has a refractive index of, let's say, 1.4, and I place it into a liquid that has 1.4, there's no speed bump. So since there's no speed bump, there's no bending of light. If there's no bending of light, that means that that object is going to look invisible. So it's a pretty cool trick. Magicians love using that. If you've ever seen any magic shows where they make things disappear, they are using refractive index. They're basically taking two objects that have the same refractive index. When placed side by side or within one another, that light is not going to be obstructed in any way. So your eye has nothing to catch onto, and therefore it will appear to be invisible to you. So that's kind of a cool trick there. One thing we definitely want to remember for a test is that the Beck line is always going to chase the higher number. So whenever I ask you, where is the Beck line, always look for your higher number, and that higher number is going to tell you whether it's going to be inside, is it going to be outside, or is it going to be altogether invisible. So in this picture here, this is an actual forensics picture taken from a microscope. We would have done this lab when we get back. Hopefully we can get to doing this lab. It's a really simple lab, really quick setup as well. So what I've done here is I've placed two pieces of glass into two different liquids. On the one on the left, so let me label it left here, except I don't know how to use that. Okay, there it is. On the one on the left here, this particular piece of glass, both pieces of glass are exactly the same. They're not the same piece. You're going to notice there's a little divot right here. These are two of the same glasses from the same bottle. So all I did here was I broke a piece of glass on a bottle, and I placed it into two different types of mediums. So in this case, I have water on the left, and so I just plunked that glass right in a little drop of water and put it under my microscope. You would use a compound microscope for this one. Stereo microscope does not allow you to see the refractive index as well, basically because the light source is a little too wide. So compound microscope is going to work the best here. And what we're going to see is that the glass has a 1.5. So I'm going to write 1.5 in there. There are no units, and I should have shown this before, but there are no units because they actually canceled in the earlier part because of the fact that the speed of light is meters per second, and the speed of light in the medium is also meters per second, so those cancel. So remember, we have the speed of light in air divided by the speed of light in the medium. And so anyways, because that would be meters per second over meters per second, those guys cancel. So there's no units on this one. That's actually really cool for you guys. You don't have to remember what they are. So we see that on our left-hand side, we have our glass, and it has a refractive index of 1.5. You can't see the water on the slide here, but let's just kind of pretend I poured some water in there. So there's water here, water there, water everywhere. And so the refractive index of the water, as I've labeled right here, is 1.33. So because that light, as it's coming in, so our light is going to, I'll draw it in yellow, our light is going to come in, and it's coming in on the right here, and it's not going to hit any kind of speed bump there because the water has the lower refractive index, so it's going to keep going right on through into the glass. When it gets into the glass, it's going to be trapped by that higher number, And we're going to see this white line that's kind of going across all around here. So if I'll trace it out. So that white line there traps it on the inside. That's our Beck line. So the answer to the one on the left is, where is the Beck line? It's going to be on the inside. Why is it on the inside? Because the Beck line always chases the higher number. Why? Because that higher number has that strength to really capture the light. On our right, let me go ahead and erase this little divot. We're going to have our light coming in also from the right. So I'm going to have our light come in. I'll make it yellow again. Our light's going to come in, but in this case, we see that the oil is 1.54. So we have 1.54 hanging out on the outside here. And we have 1.33. Oops, excuse me. No, that's wrong. It was actually 1.54. 1.54 on the outside, 1.50 on the inside. So even though there's just a slight difference right here, just that 0.04 difference between the glass and the oil, that is going to be enough to trap the light. So the light can't pierce through that oil. And so what it's going to do is it's going to come on in, it's going to hit that barrier, and then instead of going into the glass, it's going to stay on the outside with the oil. And why? Because that Beck line is always going to trace that higher number. So on this side, it's going to be on the outside. All right. So let's draw an example for ourselves. So where will the Beck line fall? For example 1, we have a polyester fiber, and it has a refractive index of 1.57. So we want to highlight that. And we know that's our fiber. That's going to be our CM. It is placed into a castor oil with a refractive index of 1.4. So we have another refractive index there. Where will the Beck line be? So when we look at this question, you might think, okay, do I have to do a guess for this one? And the answer to that one's no. I'm actually asking you guys for a qualitative answer, meaning I want to know a where, not a how many or how much. So because I'm asking you for this qualitative answer, you're not going to be required to do a guess. So I'm going to go ahead and put A right here. I'm going to draw it in black though, just because it has a thinner line. And I'm just going to draw that fiber. So first thing I'm going to do is just draw my fiber here. A little rectangle, doesn't have to be anything special. And I'm going to draw it in oil. So I'm just going to put a little puddle of oil around it. All right, so there's our oil. We know that the refractive index of our fiber is 1.57. And we know that the refractive index of the oil on the outside here is 1.482. I'm just going to put 1.48. And so we're going to ask ourselves, which is the higher number? Okay, so the first thing you want to do is just identify where is that higher number. And right off the bat, we see that that higher number, let's do yellow, do green, is that 1.57. So the answer to this question is where is that Beck line going to be? It's going to be on the inside with that higher number. Why? Because that light's going to come on in. Here it comes. It's going to be able to pierce that oil pretty easily. But when it gets in there, it's going to bend inside, and it's going to be on the inside of our fiber. So the answer for A is inside. What about B? So we're going to take that same fiber, draw a little picture. That same fiber is going to be placed into bromoform, which is a type of chemical. And this time, bromoform has a refractive index of 1.6. So I'm going to draw my little puddle here. I know that my bromoform has a 1.6. The little point doesn't come out very good, but it's right there. And I have my fiber, which we said earlier was 1.57. So again, we're going to ask ourselves, where's the higher number? So on this one, we see that the higher number is outside of the fiber. inside of the bromoform. So since it's on the outside number, that means that the Beck line is going to also be on the outside. So the answer for B is on the outside. All right, so again, what are we looking for on this one? We're looking for which of the two mediums has the higher refractive index. When you know which one is the for a higher refractive index, you know then that that's where your Beck line is going to be. So if it's the inside one, if it's the fiber on the inside of the oil, it'll be on the inside. If the oil has a higher refractive index, it will be on the outside. What happens if the refractive indices are the same? It's invisible, so there is no Beck line. So if they are the same, if I had said 1.4 and 1.4, there would be no Beck line. And that might show up on a test, so we definitely want to make sure we know where our Beck lines are going to show up. This originally would have been a short answer test, but on this one it will be multiple choice. So I will be asking this question for sure. So make sure you guys really highlight this slide, put a star next to it, watch this video part over again, but that is going to be on the test. All right, so when do we use guess? We're going to use guess to calculate the refractive index when you are given the speeds of light. So in example 2, we see that light travels through air at a rate of 300 million meters per second before it enters water, where it's going to slow down to 225 meters per second and calculate the refractive index. So I want to go ahead and identify what are my numbers. I have a rate of 300 million meters per second. And I know that's in air, so that's good to know. And I have a rate of 225 million meters per second. And I know that that one is going to be in the water. So the first thing I want to do is go ahead and set up my guesswork. I'm going to set up my G. Oops, let me use the right thing. I'm going to set up my G. And for my G, I know that the speed of light of air is always 300 million meters, so we always use 300 for air. So I'm going to say C of A is equal to 300. The speed of light in the water, I'm going to say C of W, is equal to 225 million meters per second. What's the U then? The U is going to be the part where it says calculate. So I know that that's what they want me to do. So my U is going to be to calculate the refractive index. Big question mark there because I don't know what it is yet. I do have a formula for it. I'm going to stick that formula right there. And I know that refractive index is equal to the speed of light in air divided by the speed of light in water. Okay, and I'll give you a second right there where I'm going to go ahead in just a minute. I'm going to erase that so I could show you guys the two S's. So I'm going to go ahead and see if I can get away with just erasing this part. I'll leave the equation up. Okay, that's enough there. All right, so I'm going to go ahead and start substituting in with my first S. I'm going to go ahead and say refractive index is equal to 300 million meters per second divided by 225 million meters per second. And my math people here are probably wondering why I left all those zeros in there. You're like, kill the zeros. And so I'm going to go ahead and do that actually. First thing I'm going to get rid of are those meters per second. So we know that those can cancel. So those are gone. I've got a set of 3 zeros here and 3 zeros there. I'm going to get rid of those. I'm going to do the same thing here. And now I have 300 divided by 225. This is totally doable. You can always do that. Just make sure, though, that you have your place setting set up correctly so that in case maybe the number is over 300 million, maybe like let's say it's me think of another one. Like if it has a different place, so maybe it's only 30 million versus 300 million, then you might get kind of confused on that. So just make sure that everything lines up when you guys cancel the zeros. But in this case, it works out perfectly. So I'm going to do 300 divided by 225. And for my next S, I'm just going to have that number as 1.33. And there's no units because they canceled before. And so my answer is 1.33. So we have a fiber has a refractive index of 1.53 and it's placed into water. Where will the Beck line be? So from the last slide, just really quick, we saw that the water gave it a Beck line of refractive index of 1.33. So we're going to need this number for our next problem. So we know that the refractive index is water. So we're going to go ahead, again, we're not given any speeds of light here. We're just given some refractive indices. So let's go ahead and underline that. We have a refractive index of 1.53. And you might be asking where that water one went, but guess what? It was in the last problem. So we're going to go ahead and draw a picture. So I'm just going to draw my fiber. And my fiber has a 1.53 refractive index. I'm going to put it in some water. I'll even use blue. And my water has a 1.33 refractive index. And the question is, where is it going to be? So then we look for the higher number. So really quickly, we see that 1.53 is higher than 1.33. So that means that Beck line is going to be on the inside. And I kind of did these flipped. Now, one thing I kind of was trying to show you here is that you really can't answer question 1 without actually doing the model. It's a lot easier to kind of draw the model in the beginning when you're kind of figuring it out. So here's the model for part 2, and the answer for part 1 is that Beck line is going to be on the inside. Why? Because that light is going to get trapped by that higher refractive index. So it's unable to pass through any further, and so it's going to get stuck in there. A couple of other tests worth looking at are the Fourier transform infrared analysis, also known as FTIR. Again, these are just going to be vocabulary words. You might see them as selections on the multiple choice to kind of throw you off. But overall, I'm not really going to be doing too much with Fourier transform infrared analysis, or FTIR. Same thing with optical microscopy. Optical microscopy is another type of microscopy where we're using polarizing light. So instead of just using a white light, we're using a polar light, similar to what you would see with your polarizing sunglasses. Again, not going to be something we're going to focus on the test, but you might see them as selections in your multiple choice. So if you see them and you're kind of like, what are those? Skip them. That's not the right answer. One thing I may actually do, though, on the test is I may put the pyrolysis gas chromatography on there. We are going to do a lot in chromatography on the next EQ. So chromatography is a separation technique. And I just kind of want you guys to look at the root for pyro. And so pyro, most of us know, is someone that likes to play with fire. It's the street term for it. But pyro actually does mean fire. So when you see pyrolysis, we're doing a separation through a controlled burning. So unlike your burning test that you guys did with your Bunsen burners, that was modified control. This one is extremely controlled. We're controlling temperature as well, and as well as the rate of separation. And so we can separate our fibers into their little components and actually see molecularly what they are. Not too much on the test on this one, but I do want you guys to kind of realize that pyro means fire, and then chromatography is separation. So it's a process of separation through fire. As long as you can kind of remember that for your test, you'll be okay. The test will be open note, so that'll be good for you guys. If you have any questions or concerns, please feel free to contact me, reach out, and I will get back to you as soon as I can. And just let you guys know, stay safe, keep that social distancing at 6 feet. And I miss you guys, so hopefully I'll get to see you guys later on, sooner than later, and I'll talk to you later.